Welcome back to Silicon Frontier. I'm your host, and as an engineer, I love taking things apart to see exactly how they tick. Today, we're doing just that, with the fundamental architecture powering modern technology. We're going to look under the hood of the hardware that makes everything from high-end graphics to the artificial intelligence revolution possible. I'm talking, of course, about the GPU. Now, you might be wondering, we rely on massive computing power for our most advanced applications today, right? So, if our standard central processing units, the CPUs, are already incredibly powerful marvels of engineering, why do we even need a separate graphics processing unit? I mean, why build a chip with thousands of tiny cores instead of just making a few really massive, powerful ones? Well, let's break down the silicon step by step to find out. First, we'll look at the processing power paradox. Then, we'll compare CPU and GPU architectures. After that, we'll talk about mastering parallel processing. Dive deep inside the GPU silicon, see exactly why AI runs on GPUs, and finally, unpack the memory hierarchy bottleneck.
All right, let's jump right into part 1, the processing power paradox, and the limits of the CPU.
Let's start with a system you're likely very familiar with, the general-purpose processor. A CPU is fundamentally designed to be a master of complex, sequential tasks. If you look at the physical silicon, CPUs contain a relatively small number of highly powerful, sophisticated cores. Each of these cores is engineered to execute complex instructions and make rapid decisions. They are exceptionally good at running your operating system, managing various background applications, and executing sequential programs. When you double-click an app, your CPU has to rapidly read files, check permissions, allocate system memory, and run a whole sequence of distinct instructions. The entire architectural philosophy here is focused on low latency. That means the goal is to finish one specific, really complex task as absolutely fast as possible before moving on to the next.
But modern workloads introduce a pretty massive paradox. Applications like rendering photorealistic graphics or processing data for AI models completely break the CPU's traditional paradigm. Instead of asking the processor to complete one highly complex task incredibly quickly, these workloads ask the processor to perform millions of relatively simple, simultaneous calculations. Your CPU has incredibly powerful workers, sure, but it simply doesn't have nearly enough of them to handle millions of tasks at the exact same time. Which brings us to part 2, CPU versus GPU architecture, and the battle between latency and throughput.
To solve this massive computational bottleneck, hardware engineering had to completely shift its focus. Think of it this way. A CPU is like a small team of highly specialized, expert engineers. If you have a really difficult, unique problem to solve, this is the elite team you want. But a GPU is designed completely differently. A GPU is like a massive factory with thousands of workers on an assembly line. Each individual worker might only know how to perform a very basic specific operation, but because there are thousands of them working simultaneously, together they can produce a massive amount of total output.
And this highlights the core technical distinction in hardware design, latency versus throughput. A CPU optimizes for latency, getting one job done instantly. A GPU optimizes for throughput, finishing a massive pile of work altogether. Let me give you a practical analogy. If you need to wash a single car, you want that expert team of detailers to get it done perfectly and quickly, right? That's low latency. But if your goal is to wash 1,000,000 cars, an expert team of 3 people will literally take years. You need a massive factory with thousands of workers washing cars simultaneously. That is high throughput, and that is exactly what the GPU is engineered to deliver. Let's move on to part 3, mastering parallel processing and how we actually divide the work. This massive factory approach relies on a foundational concept in computer science. Parallel processing is simply the ability to complete a staggering amount of work at the exact same time by taking a huge problem and dividing it among many smaller processing units. Imagine you're processing a high-resolution digital image. That image is made up of millions of individual pixels. And to, say, apply a filter to the image, every single pixel needs mathematical calculations applied to it. So how do our 2 processors handle this? Well, a CPU might try to process those pixels sequentially, calculating pixel 1, then pixel 2, then pixel 3. It moves incredibly fast, but it's still operating one after another. A GPU takes a completely different execution approach. It divides the image into thousands of smaller chunks and deploys thousands of threads to process different pixels at exactly the same time. Simultaneous execution versus sequential execution. That right there is the true power of parallel computing. Okay, part 4. Inside the GPU silicon and the hardware hierarchy. Let's zoom way in, microscopically, and look at how this silicon is actually structured to manage all of these simultaneous threads. A modern GPU is not just one giant flat processor, it's a highly structured logical hierarchy. The overall GPU chip is broken down into smaller processing groups called streaming multiprocessors, or SMs. These SMs are the fundamental building blocks of the architecture. Inside each SM, you have the physical execution units, often referred to as cores. And these execution cores manage the thousands of individual software threads that actually do the data processing. Multiple SMs work in concert to give the GPU its massive computing power.
And to orchestrate all of this, the GPU utilizes a brilliant execution model known as SIMT, which stands for Single Instruction Multiple Threads. In an SIMT architecture, the controller issues just one single instruction, for example, add two numbers together. But instead of one core doing that once, many different threads execute that exact same instruction on completely different pieces of data simultaneously. Imagine adding two massive arrays of numbers together. Instead of processing element 1 then element 2 sequentially, SIMT allows thousands of threads to grab their respective elements and add them all together in a single clock cycle. It's incredibly elegant. Which perfectly sets up part 5, why AI runs on GPUs. Once you grasp SIMT and massive parallelism, the hardware's intimate connection to modern artificial intelligence becomes crystal clear. When you interact with a modern AI model, whether it's processing natural language or generating a brand new image, you are triggering an astronomical amount of computation. We are talking about billions upon billions of repetitive mathematical operations happening behind the scenes in milliseconds. The mathematical backbone of artificial intelligence primarily involves operations like matrix multiplication, passing data through neural network layers, and processing massive, standardized datasets. What makes these workloads so unique is that they are highly parallel. Matrix multiplication is essentially just thousands of independent addition and multiplication problems. Because a GPU is designed precisely to perform thousands of identical calculations on different data points at exactly the same time, it is the absolute, perfect, undisputed foundation for AI workloads. A standard CPU simply cannot keep up with this level of throughput. Finally, let's look at part 6, the memory hierarchy bottleneck and feeding the cores.
We've talked a lot about processing power, but listen, having thousands of execution cores doesn't mean anything if you run into a bottleneck somewhere else on the chip. As an engineer, one of the most fundamental rules of computer architecture is this: a processor waiting for data cannot perform useful work. If you have thousands of workers in a factory, but the conveyor belt bringing them parts is moving at a snail's pace, your factory stops. The processors sit idle. And here is where the ultimate bottleneck happens in parallel processing: starvation.
To prevent the cores from starving, hardware engineers have meticulously built a strict GPU memory hierarchy. Closest to the cores are registers, which hold data right where the calculation happens, offering lightning-fast access. Next is shared memory, allowing threads within the same block to communicate and share data incredibly quickly. Then we have cache memory, and finally, the large pool of global memory. The key to extracting maximum performance from a GPU isn't just writing parallel code, it's efficiently managing this memory hierarchy to ensure that massive factory of execution cores stays constantly fed with data.
Ultimately, the incredible capabilities of modern computing rest entirely on this distinct difference in architectural philosophy. A CPU is designed to be a powerful problem solver. A GPU is designed to solve thousands of similar problems together. By shifting the engineering focus from the latency of a single thread to the total throughput of thousands of threads, the GPU unlocked the massive parallelism strictly necessary to power today's graphics and artificial intelligence. But understanding this high-level architecture is really just the beginning of our journey into the silicon. In our next explainer here on Silicon Frontier, we're going to dive even deeper into the chip. We'll open up the streaming multiprocessor, the true beating heart of the GPU, and analyze how it physically schedules and executes all these threads. Until then, keep questioning the technology inside your hardware, and ask yourself, as our software demands even more parallel throughput, how will the physical limits of silicon need to adapt next? Thanks for joining me, and I'll see you in the next explainer.